In this video, we're going to look at finding the limit of a linear first-order recurrence relation, if it exists. So here it says start writing out the terms of these sequences to help determine if a limit exists. Okay, so our first one here then, un plus 1 is equal to 5un plus 6, and we're given our first term to get things going. So let's make use of the calculator to do this efficiently. Okay, I'm going to start by typing in 10, my first term, and then hitting equals. And then that will store it in the answer button. So then I'm going to type out my recurrence relation, where it's going to be 5 times the answer plus 6. Okay, because the un, we want that to be the answer each time. So 5 multiplied by the answer plus 6, and then click equals, and we get 56. Okay, and that is going to be u2. Then u3 we will get if we click equals again. So we get 286. Then u4 if we hit equals again, 1436. And if we do it again for u5, we get 7186. So I think it's pretty clear this sequence is not going to have a limit. Okay, it seems to be getting bigger and bigger and bigger, and you can see the differences between the two terms each time is getting larger and larger. Okay, so for our first one, I think we can conclude the limit does not exist. So let's try our second one then. So for this one, our first term is still 10. Okay, and the only change in the recurrence relation is we now have a 0.5 here instead of a 5 previously. Okay, so we're going to click 10 and hit equals again to store it in the answer button. And then we're going to type out our recurrence relation, but I'm going to replace the un with the answer button. So I'd have 0.5 times the answer, and then it'll be plus 6. Okay, so what we would get for u2 would be 11. So that's u2. And if I want u3, I'm just going to click equals again. So this time I would get 11.5. And if I hit equals again, I get u4, which is going to be equal to 11.75. And then if I hit equals again, we get u5, which is equal to 11.875. And then click equals again, and I get u6, which is going to be equal to 11.9375. And if we hit equals again, we're going to get that u7 is equal to 11.96875. So it appears we do seem to be approaching a specific value, because if we look at the difference between any two terms, this difference seems to be getting smaller and smaller every single time. And it seems the value that we are approaching is 12. Okay, so we can say that for this one, the limit is equal to 12. Now what we have to think about is why has it converged to a limit in the second one, whereas in the first one it didn't? Well, it's all to do with the difference. The fact that the 0.5 is written here multiplying the un, whilst there's a 5 up here. Because if we're multiplying by 5 each time, we're making our terms bigger. Okay, whereas if we're multiplying by 0.5 each time, we're making our terms smaller. So it's all about that value multiplying the un when you have a recurrence relation of this format here. So what we require is that this number here, multiplying the un, has to be smaller than 1. That's how you make numbers smaller by multiplication. Okay, so the 0.5 is clearly smaller than 1, whereas the 5 up here is greater than 1. But we have to also think, what is our lower limit here? Because smaller than 1, that's still an infinite amount of numbers, okay, going off in the negative direction. Well, you'd want it to be greater than negative 1. Okay, so I'm going to write greater than negative 1. That's what we want the 0.5 to be. Okay, because if you're going smaller than negative 1, like negative 2, you're going to be increasing the size of a number, but in the negative direction. Okay, so for this sequence up here, we were going off to positive infinity as we sort of kept going on. Whereas if we changed a 5 to a negative 5, we'd be going to negative infinity instead. But as long as we're between 1 and negative 1, we should converge to a specific value. So let's write out a generalization. So here we got the general format of the recurrence relation we are considering. Okay, so something of the format un plus 1 is equal to some multiple of un plus some constant b. Okay, and what we require is that this value m here has to be between 1 and negative 1. So I've got to say m has to be smaller than 1, but it's got to be greater than negative 1. In this scenario, then the sequence will converge. Now let's have a think about how we can find our limit without generating the terms of the sequence. So we got the same recurrence relation we had before, the one that converged to 12, but the question is, how could we have got 12 without writing out all those terms of the sequence? Okay, is there a direct method? Well, what we have to consider is the limit of un as n tends to infinity. Now, if the sequence is going to converge, the value of our terms un are going to go towards a specific value. So therefore, we can say that this limit here is equal to L, where L is some defined value, which is going to be our limit. Now let's also consider the limit of un plus 1 as n tends to infinity. So remember, un plus 1 is just the term after un. So if un is tending to this limit L, then un plus 1, the term afterwards, should also be tending to this same limit L. Therefore, I can say that this is also equal to L as well. And this is going to be quite handy to help us figure out what the limit of a sequence is using its recurrence relation. So let's have a go using this one here. What I'm going to do is take the limit of both sides of my recurrence relation, because that's going to be the limit of my sequence. So I'm going to write lim and an n tends to infinity of un plus 1, my left-hand side, and that should be equal to the limit as n tends to infinity of my right-hand side, which is 0.5 un plus 6. So 0.5 un, and then we got plus 6, which we should put in brackets because it's multiple terms, like that. The idea is, if the left-hand side is equal to the right-hand side, then the limit of the left-hand side should be equal to the limit of the right-hand side. Now let's have a think about what I can do with this equation here. Well, we know that the limit of un as n tends to infinity is just equal to L. So therefore, I can replace that with an L. Okay, so I would write L is equal to the limit as n tends to infinity of the 0.5 un plus 6. Now let's have a play around with the right-hand side. Okay, and the first thing I know about the right-hand side is this plus 6 does not involve any n. Therefore, we can take this out of our limit because it's not influenced by the n going to infinity. So therefore, we would get that L is equal to the limit as n tends to infinity of the 0.5 un, and I'm going to write a plus 6 outside. So it's now independent of the limit because it was independent of n. So then what we could also do is recognize that the 0.5 in my limit here is independent of n, so we can factorize that out. So we would get L is equal to 0.5 of the limit as n tends to infinity of un plus 6, like this, where the plus 6 is outside the limit. Then if we look at our limit now, we should recognize this scenario because we discussed it earlier on. It's the limit of un as n tends to infinity, which is equal to L. Therefore, I can replace it with an L, so I get L is equal to 0.5 multiplied by L plus 6, like that. Okay, now I have an equation which I can solve to figure out what this value of L actually is. So let's just write the equation over here, and before we actually solve, let's just have a think about how we could have got here a little bit quicker. If we look back at our initial recurrence relation, it does look very similar. The only difference is essentially what I've done is I've gone to the un plus 1 and the un, so both of my subscript terms, and they've both been replaced with L's. Okay, so I can immediately go to this line of working here, and then I can quickly solve for L. So if we subtract 0.5 L to the other side, we get 0.5 L is equal to 6. And then if you divide by 0.5, well then we're going to get L is equal to 12, which is the same answer we got by generating the terms of the sequence using the calculator. But this is clearly a much faster method. So let's have a go at another question where we use this method straight away. So we got our recurrence relation here, and we need to explain why this sequence has a limit as n tends to infinity, and we need to calculate the value of this limit. Well, in terms of why it has a limit, that relates to the value multiplying our lower subscript term, okay, which is the 0.8, and this 0.8 is smaller than 1, but it's greater than negative 1, so we can say therefore the limit will exist. Now let's actually find my limit. So what I need to do is go to both of my subscript terms, so the un plus 1 and the un, and we're going to replace it with an L, because the limit as n tends to infinity of the un plus 1 is equal to L, which is also equal to the limit as n tends to infinity of un. Okay, so I would get L is equal to 0.8 L plus 4. And then I can just rearrange and solve. So let's subtract the 0.8L to the other side. So I'd get 0.2L is equal to 4. And then we just need to divide by 0.2. So we would get L is equal to, and the answer would be 20. Okay, so the limit of our sequence is 20. And you could have found that using the calculator. However, this method is going to be much faster. So for the basic scenarios we've been looking at, where un plus 1 is equal to some value multiplied by un plus some other value, where m is a value between 1 and -1, you should always be able to find the limit with this method. Now, we won't necessarily ever reach this limit, as in there might not be a term in the sequence that will be equal to 20. However, we will approach this value. Now, for more complicated recurrence relations, you won't be able to be sure that the limit does exist even if you find a value for L, okay, because actually whether you actually reach that limit will depend a lot on what the first term in the sequence is, which can have quite a big impact. However, for the ones that we've considered here, regardless of what the first term in the sequence is, the limit is going to be 20. Let's have a look at another question. So two sequences are defined by these recurrence relations here. So we've got one for un and one for vn. If both sequences have the same limit, we need to express p in terms of q. So if both sequences have the same limit, let's call that limit L. Then what we can assume is that the limit, as n tends to infinity, of un plus 1, un, the vn, and the vn plus 1 are all equal to L. So what I can do is go to both recurrence relations and replace all of my subscript terms throughout with L's. So what I'm going to get for our first one is L is equal to 0.4 L plus P. And then for my second one, it is going to be L is equal to 0.8 L, and it's going to be plus Q like that. So we got two equations that include L's and P's and Q's. Okay, we need to express P in terms of Q. So this letter L that I picked, we need to eliminate it. So what I'm going to do is go to both equations and try and make L the subject. So I'm going to subtract 0.4 L to the other side. So I would get 0.6 L is equal to P. Then for this one, subtract the 0.8 L. So I get 0.2 L is equal to Q. And then for this one over here, we're going to divide by 0.6. So L is going to be equal to 10 over 6p, which simplifies to 5 over 3p. And then for my other equation, we're going to divide by 0.2. So we would get that L is equal to 10 over 2q, which simplifies down to just 5q. So now we've made L the subject in both equations, so we can now equate both equations. We can write that 5 over 3p is equal to 5q. And now we have an equation just in terms of P and Q. Now, if we look at what the question wanted, we need the P in terms of the Q. So therefore, we need the P to be the subject. So I'm going to multiply by 3 to get 5P is equal to 15Q. And then we're going to divide by 5. So P is equal to 3Q, which is my final answer in this case.